is used to bring about the chemical reaction in the cell. Let us see a simple electrolytic cell consisting of two copper strips dipped in a solution of copper sulfate. Now, if we apply DC voltage to the electrodes, then at anode, copper loses electrons and goes into the solution as ions. At anode, Cu solid gives Cu2 plus solid plus 2 electrons, while simultaneously at cathode, the copper ions of solution gain electrons and get deposited. At cathode, Cu2 plus aqueous plus 2 electrons gives Cu solid. So we see that copper is dissolved or oxidized at anode and deposited or reduced at cathode. This is used in industrial purification of copper up to 99.95%. The zinc and iron impurities remain in solution as ions, while the gold, silver and platinum impurities deposit at bottom as anode sludge. Many metals such as sodium, magnesium and aluminium are produced by the electrolytic process using electrochemical reduction. We know now how the electrolytic process occurs. But how to know the amount of substances that are liberated at electrodes due to the electrolytic reaction? To answer this question, Faraday gave some laws. Let us perform electrolysis of a silver nitrate solution and deposit silver on a copper key. The key weighs 40 grams initially. How much silver will be deposited if we pass a current of 1 ampere through it for 1 hour? To answer this question, Faraday gave a law which states that the amount of any substance deposited, evolved or dissolved at any electrode is directly proportional to the amount of electrical charge passing through the circuit. The reaction occurring at cathode for deposition of silver is as Ag plus aqueous plus electrons give Ag solid. Charge on 1 mole of electrons equals Avogadro's number, Na, into charge on 1 electron equals 6.023 into 10 raised to 23 into 1.602 into 10 raised to minus 19 coulombs equals 96,487 coulombs. That is 96,500 coulombs equals Faraday's constant. Charge Q equals current I into time t equals 1 into 60 equals 3600 C. So, amount of electrons equals total charge by Faraday constant equals 3600 C by 96,500 equals 3.73 into 10 raised to minus 2 electrons. From the reaction, 1 mole of electrons reduce 1 mole of silver ions. So, 3.73 into 10 raised to minus 2 electrons will reduce 3.73 into 10 raised to minus 2 silver atoms. 1 mole silver atoms weigh 107.9 grams. So, 3.73 into 10 raised to minus 2 atoms will weigh 4.02 grams. So, the weight of the key is 44.02 grams as 4.02 grams of silver is deposited on it. Now let us conduct one other experiment. We have a solution of dilute sulfuric acid, a solution of copper sulfate, and a solution of silver nitrate connected in series. If we pass the same amount of current through all three solutions, what will be the masses of different substances liberated or deposited in all three solutions? This question is answered by Faraday's second law. Faraday's second law states that the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Now, the chemical equivalent weight is equal to atomic mass of metal divided by number of electrons required to reduce the cation. The equations at cathode for each electrolytic cell are In cell 1, we have H plus aqueous plus electron giving 1 by 2 H2. In cell 2, we have Cu2 plus aqueous plus 2 electrons giving Cu solid. In cell 3, Ag plus aqueous plus electron gives Ag solid. 1 Faraday gives 1 mole of electrons. 1 mole of electron gives half mole of hydrogen gas. Half mole of hydrogen gas equals 1.008 gram. 1 mole of electron gives half mole of copper. Half mole of copper equals 63.5 by 2 equals 31.75 gram. 1 mole of electron gives 1 mole of silver. 1 mole of silver equals 107.9 grams. So, 1 Faraday of charge will liberate about 1 gram of hydrogen, 31.75 gram of copper, and 107.9 gram of silver, which are the gram equivalent weights of these elements. Thus, Faraday's laws help in quantitative description of electrolysis. Let's see what products we get on electrolysis of copper sulfate solution with copper electrodes. The reactions at electrodes are: at anode, Cu solid gives Cu2 plus solid plus 2 electrons. At cathode, Cu2 plus aqueous plus 2 electrons gives Cu solid. As we see, pure copper will be deposited at cathode. Such electrodes which participate in the reaction are called active electrodes. The reactions at electrodes are: at anode, the reaction that occurs is H2O liquid gives 2H plus aqueous plus half O2 plus 2 electrons. At cathode, Cu2 plus aqueous plus 2 electrons gives Cu solid. So as we see, pure copper will be deposited at cathode and oxygen is liberated at anode. This is because of the higher oxidation potential of oxygen than sulfate ions at anode and higher reduction potential of copper than hydrogen at cathode. Such electrodes which do not participate in the reaction are called passive electrodes. Here we have seen that the choice of electrodes changes the products formed during electrolysis depending on the reduction potentials of the components. Now let us take a look at what is happening at anode. The reactions competing against each other here are: Cl minus aqueous giving half Cl2 gas plus electrons. The standard potential of this reaction is 1.36 volts. 2H2O giving 2H plus and 2OH minus aqueous. And the 2OH minus further give H2O and half O2 with 2 electrons. The net reaction becomes H2O giving 2H plus plus half O2 gas plus 2 electrons. The standard potential for this reaction being 1.23 volts. The reaction at anode with lower value of E0 is preferred and therefore water should get oxidized in preference to Cl minus aqueous. But due to overpotential of oxygen, the first reaction is preferred and chlorine gas is liberated. Two different ions are competing for reduction here. Na plus aqueous plus electron gives Na solid. E cell 0 equals minus 2.71 V. H plus aqueous plus electron gives half H2G. E cell 0 equals 0.00 V. The reaction with higher value of E0 is preferred for reduction and therefore the reaction at the cathode during electrolysis is H plus aqueous plus electron gives half H2G. NaCl aqueous gives Na plus aqueous plus Cl minus aqueous. Cathode, H plus aqueous plus electron gives half H2 gas. H2O liquid gives H plus aqueous plus OH minus aqueous. Net cathode reaction H2O liquid plus electron gives half H2 gas plus OH minus aqueous. Anode Cl minus aqueous gives half Cl2 gas plus electron. Net reaction NaCl aqueous plus H2O liquid gives Na plus aqueous plus OH minus aqueous plus half H2 gas plus half Cl2 gas. So, again we see that many factors affect the products formed during electrolysis depending on the reduction potentials of the components.